Hello, and welcome to today's webinar, which is entitled Controlled Channeling Contrast Imaging, a New Perspective for Dislocation Analysis in Bulk Samples Without a TEM. I'm joined today by our expert speaker, Stefan Zefferer, who is a group leader at the Max Planck Institute for Sustainable Materials, and also Rishi Bail from Zeiss Research Microscopy Solutions, and they're going to be taking you through this talk today. Following the talk, we will have a question and answer session lasting approximately 10 to 15 minutes. And that's your opportunity to ask questions to our expert speakers about the content of their talk. So please feel free to drop your questions into the Bizabo interface with which you're currently interacting. And I can put that to our expert speakers at the end. So for now, sit back and enjoy. I'm going to let the guys take it away. I hope you enjoy it. I'm certainly looking forward to it, and I'll see you for the Q&A session. Take it away, please, guys.
Controlled electron channeling contrast imaging. My name is Rishi Bail, and I'm the business sector manager for engineering materials in the material science sector at Carl Zeiss Microscopy. Thank you for joining in to attend this webinar. I will be jointly presenting on this topic with our close collaborator and world expert, Professor Stefan Zefferer from the Max Planck Institute of Ion Research in Dusseldorf. So before I jump in, this is our brief agenda. I will be covering the base SEM microscope configurations that enable the cutting-edge ECCI technique, and then go through some basic SEM fundamentals necessary for ECCI. After my short intro section, Stefan will give us a deep dive into the topic. Now, we all have either come across this famous tetrahedron, also known as the material science paradigm, or the material science tetrahedron. The idea is that a material's microstructure, its properties, performance, and processing are all connected. And at its core lies characterization that makes the link to all four of these points. As an example, look at the schematic on the right hand side, which is of a metal. From macro to micro scale, there are a variety of features ranging from macro scale voids, pores, grains to precipitates, inclusions, and lattice defects at the nanoscale. All of these properties are linked, and microscopy is at the center stage if we want to understand their interplay. Now, to address the challenge seen in the example earlier, we have a wide range of imaging modalities one can use. Zeiss offers a wide range of these, going from light to X-ray to electron microscopy towards the right-hand side. This also corresponds to the imaging resolution. As we go from left to right, we get increasing imaging resolution. So today we shall focus on the FESEM product line, or the field emission SEM, on which the entire imaging modality of ECCI is based. The FESEM further has three different flavors catering to the needs of a typical microscopy lab, ranging from general purpose imaging, which you see on the left hand side, specific analytical experiments in the form of the Gemini 460, which is at the center, and then some high-end, high-resolution, low-kV surface imaging, which is available on the 560, which is on the right-hand side. Now let's take a look at the Gemini column, the underlying technological centerpiece of these microscopes. Due to its unique design and engineering, the Gemini columns are able to achieve great imaging results. In terms of the capabilities, the column consists of specifically designed condensers that deliver the most parallel low convergence beams. We also have beam booster technology that maintains the primary beam at high tension throughout the column to ensure a stable and high brightness beam. Then we have the combination of Gemini objective lens with in-column deceleration and field-free effects on the sample surface, followed by a wide variety of high-performance detectors like the InLens, ESB, BSD detectors that deliver the best imaging results. The end result is you get superior low kV performance, you can get high voltage contrast, you can get enhanced compositional contrast, and other modes like ECCI, which we shall look into. A closer look at the Gemini columns shows us the fundamental difference between the Gemini 2 and the Gemini 3. The Gemini 2 is built for analytical imaging and has a double condenser that allows fast switching between imaging and analytical modes. We also get a high current, high resolution imaging. I will emphasize that due to this design, the Gemini SEM 460 microscope is best suited for cECCI imaging. The Gemini 3, on the other hand, has a purpose-built, high-performance, high-resolution configuration with only a single condenser, but some advanced lens designs that couple magnetic and electrostatic lenses. This also can be successfully used for ECCI, however, 460 is much more favorable. Now let's take a look at the contrast in electron microscopy imaging. This image shows many contrasts. From top to bottom, we have material contrast due to different atomic numbers, then topographical contrast, and lastly, channeling contrast. Among the three, as shown by the increasing bar from bottom to top on the right hand side, the channeling contrast has the weakest signal strength, and hence it needs to meet some special conditions for best imaging. Now, without drilling too deep and going over all of the imaging capabilities of the Gemini SEM, I'd like to give you a quick overview of various things that you could achieve. We have the low kV imaging at the top that shows how we can achieve best surface imaging results by optimizing the low kV. In the bottom row, the left image shows optimizing contrast through different detector to differentiate different phases in ferrocerium alloy. And the center image shows use of the ASB detector to give superior contrast on a titanium aluminum alloy. Lastly, we have an example with sweet spot imaging, which allows you to play with contrast based on a combination of working distance and kV. So here you can see, as we change the working distance, you can see different phases. Now let's talk about the main topic of today's presentation, which is ECCI. ECCI stands for Electron Channeling Contrast Imaging, which is a mode for quantitative characterization of deformation structures using an SEM. It is based on the relative orientations of crystal lattices and the incident electron beam to produce the desired backscattered signal. With this technique, you can image dislocations, stacking faults, and other crystallographic defects at a very fine scale in bulk samples on the SEM without the need for complex TEM sample prep. We have two nice examples shown here. One is a subgrain boundary in a creep sample of uranium dioxide, and the other is a nickel superalloy imaged using ECCI. Now, we do have a unique way of conducting ECCI, and we call this cECCI, where the C stands for controlled, in which the illumination of a certain grain is controlled using a targeted sample tilt that is evaluated using a specialized software that couples eBSD data and produces the simulated channeling planes. This is really the key to an efficient, fast, and easy ECCI method, which Stefan will cover in great detail. Now, just to recap on the key enabling technological features of the microscope that make ECCI possible, these are the main characteristics that are necessary. So a small beam convergence, a small beam spot size, a high beam current, and a high beam stability, along with sensitive and quick BSE detector. All of these are provided in the Gemini SEM microscope. The slide here shows you the breakdown of what a typical controlled ECCI package comprises of. All of these components are necessary for running a successful experiment. So you would need the Gemini microscope, the Gemini SEM microscope, a 6-axis stage, a dedicated pole piece mounted BSD detector, an eBSD detector, and finally the TOCA software, which is designed and developed by Stefan. With that, we come to the end of our first section. I would at this point like to pass on the presentation to Stefan for a deeper dive into controlled ECCI imaging. Thank you, everyone. Over to you, Stefan.
Hello, everyone. I'm Stefan Zefferer. I'm a group leader at the Max Planck Institute for Sustainable Materials, former Max Planck Institute for Iron Research in Düsseldorf in Germany. And it's my pleasure to talk to you today about an SEM technique called electron channeling contrast imaging. So let me directly switch to my presentation and organize my screen shortly a little bit. So I will introduce the technique electron channeling contrast imaging, shortly ECCI, which is an SEM-based technique for the observation of crystal lattice defects. That means, for example, dislocations, stacking faults, grain boundaries, and so on, in metals, in minerals, and in other crystalline materials. I'm doing this talk in collaboration with Carl Zeiss Microscopy, who is actually supplying a very well-suited microscope for that task. Let me also switch shortly my pointer to a laser pointer so I can more easily show for you. So what am I going to show to you? I will first start with an introduction to the technique. That means I will show you what is ECCI generally and what is new about it. I will then compare the ECCI technique, which is an SEM-based technique, with the traditional TEM-based techniques for defect observations as an introduction. I will then go just a little bit through the theory, show you how the electron scattering mechanisms and electron channeling belong together. I'm then explaining how we see defects by ECCI, meaning stacking faults, dislocations, and a little bit how we model, or how we could model defect images. And then I will show a couple of examples from different materials and finally conclude. So, what is ECCI and what is new about it? ECCI in general stands for, as I mentioned already a couple of times, electron channeling contrast imaging. And this technique is an SEM-based electron diffraction technique. And it uses actually backscattered electrons to see, that means we need a backscatter electron detector to see lattice defects in an electron diffraction technique very similar to what we do in transmission electron microscopy in TEM. Now, my contribution to the whole story is to do controlled electron channeling contrast. And this aim, I have added this little C to the ECCI acronym, which stands for controlled. And what does this mean? It means we are controlling the direction of illumination on the crystal lattice by educated tilting of the sample or the beam. That means by controlling in which direction does the electron beam arrive on the crystal lattice, we are able to actually do crystallographic analysis of lattice defects, similar to what we do in tilt experiments with the TEM. All right, so let me introduce this technique by comparing it with transmission electron microscopy. Here is an image taken from literature, from a paper of Kondo and co-workers from 2016, who observed in situ transmission electron microscopy on nanoindentation. Let me make my image here a little small, in strontium titanate in this particular case. To this aim, the group of Kondo prepared a bicrystal. Here you see a grain boundary between two crystals. They are nicely thinned. And then here at the side, you see an indenter tip placed right on the edge of that thin foil. And when now the force on the indenter is increased, you see dislocations are created. And these dislocations with increasing force become denser and denser and pile up in front of this grain boundary here. And at one moment, we get so-called pop-in event. That means that suddenly the indenter pops into the material, creates a lot of dislocation in its surrounding, and we see even dislocations creating in the neighborhood of the in the second grain of the grain, on this other side of the grain boundary. Now, this is a very very informative experiment, but it's also extremely difficult to do. You need the right thickness of your sample. You need the right orientation of your sample. You need the right orientation of your nano-indenter in order not to create buckling, but really indentation. All the lighting, the electron directions need to be correct. And then you can, I say always once in a lifetime, which is of course not perfectly true, you can create such a beautiful experiment. Now, I don't claim that we can do the same thing in SEM, at least not yet, but we can do something very similar, and that is shown here. This is, again, a nano-indent, shown in the same magnification as in this case here, 200 nanometer bar, 200 nanometer bar. This indent has been done into a bulk sample of a TWIP steel, in this case, a steel with so-called twinning-induced plasticity. And of course, during the indentation, we couldn't observe this process because the indenter is, let me see that I get that picture. The indenter is right in front of the material, so the electron beam cannot see the material in that very moment. But we can withdraw the indenter and then observe what has happened. And what we see here, all these white lines are actually dislocation lines, which have been created by the indentation into this material. You see here is one source of dislocations emitting loops. Here is another source emitting loops on this slip system here. Here are individual dislocations, some of them far out of the indentation. And this one here is stacking faults, which come from deep below, from very deep below the indentation to the indent and get up to the surface. And depending on the quality of the video here, you will even be able to see the extinction fringes on these on these stacking faults. We will see them later on in more quality. Now, this is a beautiful image. We can learn a lot from it, but we can do more than that. Because we are indenting, oh, I forgot to mention one thing, of course, as we are doing controlled illumination, we also know which diffraction vector, we'll come to this later on, which diffraction vector G has created this image. In this case, it's a 111 type diffraction vector. Now, as we have a bulk material, we are, of course, able to do many of these indentations, and that's shown here. This is a polycrystal of this TWIP steel, and you see many different crystals here, and some of these crystals have been indented, each one with 5 by 5 indentations, in order to make sure that we get the statistics of dislocation formation correct. So we can later on, after observing all 25 indents for different crystal orientations, what are statistically, stochastically created dislocations and which one are really systematically created, caused by the particular orientation of that grain. We would also be able, of course, to go to twin boundaries here, for example, or to grain boundaries here and observe how they behave. Now, important is that we have, you see, every grain has a different brightness. This grain here is particularly dark. That means the electrons don't come out again. The electrons disappear in the material. They actually channel into the material. And this is the situation where we will be able to see the dislocations. And that's also the situation which we have here, where this grain here is actually controlled to have only 111 lattice planes, channeling along 111 lattice planes. For all other grains, we need to tilt the crystal or the sample such that a set of lattice planes is activated and is channeling so that these grains turn dark, and then we are able to see the dislocations. Now, we have done that, and we obtained from many different orientations, we obtained dislocation information, and then we went still one step further. We polished these indents away, which is just a half a micrometer polishing. the grain structure stays the same because it is quite big grains. Then we charge that sample with hydrogen, and we indented exactly the same grains again. And then we can compare how do dislocations behave with and without hydrogen for storage stored in the material. And that's what I would like to show you right now. So here we have the situation of grains before hydrogen charging. Here's one orientation with the indentation direction somehow randomly inside of the orientation triangle. Then we have here Then we have here a grain which has been indented right into the cube plane of a crystal. Here is a grain indented into the 1-1-1 plane, and you see the threefold symmetry of the 1-1-1 planes. Here you see the fourfold symmetry of the 1-0-0 planes, and finally the 1-1-0 planes have a twofold symmetry. And again, for each of these situations, you see the dislocations which are created. You can study their curvature, their density, their number of sources, and all of that information. Also, how much they are split up due to a low stacking fault energy. And then we charge the sample with hydrogen, or remove these indents, charged with hydrogen, and indent it again. And this is the result here. And I go just back and forth between the two situations: without hydrogen, indentation with hydrogen, indentation without, with. And there's many things which we could see, and many things which we could analyze. I would like to point out all of these images have been taken under the same diffraction conditions with a 1-1-1 diffraction vector. And second thing I would like to point out, you see it when I go back and forth, the indentation depth is a little less deep when you indent with in the hydrogen charged material, which means the material is harder. And then you see these many particular dislocations. In this case here, these dislocations are not due to the indentation itself, but due to the charging effect, to the charging of hydrogen, which actually leads to a lattice expansion and then to the creation of these dislocations here. But all the other dislocations are due to the indentation, and we are then able to compare the situation before and after. No, I don't want to go further on that. I just want to show you another example to introduce ECCI, and that is the following here. You may all be aware of additive manufacturing, shortly abbreviated as AM, which is a way where you, for example, you use a thin layer of powder, then you use a laser and melt a certain shape into the thin layer of powder. And then after solidification, you put the next layer of powder, you put the next shape writing, and in this way you can three-dimensionally form structures. Now this laser powder bed fusion technique leads to very characteristic microstructures, which here in this case, observed by transmission electron microscopy from Wang et al., leads to this very typical cellular structures of solidification cells. You actually see cells of about 1 micrometer diameter, and these cell walls are decorated by very high density of dislocations. This is in this case stainless steel, and if we in a TEM, of course, we can easily go for higher magnification. So this here is done 5 times higher or 10 times higher magnification, and we see, for example, the chemical composition of the cell walls and the cell interior. We can do the same thing by SEM, but a little bit different. Here, this is an SEM image, which I took from a paper from Godetz and me as a co-author. And you see at the same magnification, we see the same structure. We see the typical dislocation structures lining up the cell boundaries. Indeed, in ECCI, the contrast is inversed. We have white dislocations on black background, while in TM, we usually see black dislocations on a white background in a bright field image. And in SEM, we could also go to higher magnification. But what I want to point out, in SEM, we can also go to lower magnification. And this is particularly interesting in this case of this very heterogeneous material, where we have very different appearance of microstructures, and we are able to look at very different areas. As we have bulk samples of square centimeter size, we can investigate the statistical statistical aspects of this of this microstructure. So good. With this, I hope it's clear that ECCI generally is an interesting technique to observe these features. You will see later on further results, further examples. So let me very shortly go to a bit of theory. I dropped out all the mathematics. I just show you a picture, and this picture starts like that. Imagine this is my crystal lattice. All the blue dots here indicate atoms, and they are nicely arranged like in a crystal. And now I place an electron beam onto this crystal. In vacuum, the electron beam is a plane wave, but as soon as the electrons penetrate into the material, they form a standing wave with different electron densities at different places. And this wave is displayed here as a little movie for different directions of the electron beam with respect to the lattice. So you see, for different directions of the electron beam, we see different distribution of electron intensity. So what is shown here as a wave pattern is not the electron wave, it's the density of electrons at every place. When there is a maximum, that means there are many electrons, and when there is a minimum, that means there are few electrons. And now we see two situations. One situation is that there is lots of electrons at the atomic nuclei. That is, for example, now the case here. Yeah. In this case, the electrons strongly interact with the atoms of the crystal, and we get a lot of backscattering. So there will be, in this case, a strong backscattering signal. But there's the opposite side. The opposite effect is when there are very few, when there is a minimum of electron intensity right now here, a minimum of electron intensity at the side of the atoms. And that means there's almost no interaction of the electrons with the lattice. And that means, again, that the electrons can go very deep into this lattice. And in TEM, if we would have just, if we would just have a thin foil, then, and when we observe below the sample, in TEM, we will obtain, in this condition, a very strong beam. The electrons go deep into the material. They come out on the exit surface, and we call this electron diffraction. It's for certain electron directions with respect to the lattice that we get electron diffraction. In SEM, of course, we have a thick sample. No electrons come out, but we get the backscattered electrons out. And we get very few backscattered electrons out when they are penetrating deep into the material. That means when they are channeling. While when they are backscattering, we get a lot of backscattered electrons. That means, in principle, from the interaction of atoms with the penetrating electron wave, we are obtaining a varying indirect signal of backscattered electrons. And that's what we measure in terms of ECCI. And now we can easily imagine, if we have here a dislocation inside or any kind of defect, for example, here a dislocation with one ending lattice plane, this will interfere with this regular channeling or backscattering and create contrast. And how this will be done, we will see later. Now, here we go. So I will plot here now the intensity of my backscattered electrons, independence of the angle, inclination angle of the electron beam with respect to the lattice. So let me plot here the lattice. Let me plot here the electron beam direction, the inclination angle. So, and we say, okay, at this place here, the electron beam is parallel to the lattice planes. Here it is at the Bragg angle, and on the opposite side, it is also at a Bragg angle from the opposite, from the back side and from the front side of the lattice planes. And now the intensity behavior is something like that. And actually at the Bragg angle itself, we get very little intensity. That means we are channeling here as well. While if we are parallel to the lattice planes, we actually get a strong backscattering signal. And and this is actually known from typical Kikuchi patterns. The center of a Kikuchi band is strongly backscattering, while the Kikuchi lines are showing low contrast. And this is exactly here a typical channeling pattern or Kikuchi channeling pattern. And you see here is one typical Kikuchi band which is bright in the center, corresponding to this brightness here, and has dark lines on each side, corresponding to the Kikuchi lines running parallel to it. So if we plot here the profile, we see this typical profile here. And what we actually see is along the Kikuchi lines, we obtain channeling. That's the situation when the electrons are exactly in Bragg condition, while inside of the Kikuchi lines, on the Kikuchi band, we get strong backscattering, a strong bright effect. Okay, and we can do the same thing instead of let me go back. Instead of tilting the electron beam with respect to the lattice, we can, of course, also tilt the lattice with respect to the electron beam, which would be now this situation. Now we have here different orientation of my crystal, of my lattice planes, and the electron beam arrives in a parallel fashion, and then we would get the same signal there. We would get the same behavior. So for areas where the lattice plane is just tilted such that we get that we have fulfilled the Bragg angle, we get low backscattering signal. And that's what we see here on this next picture. This is a typical polycrystalline image of I don't know, of some steel sample. I don't remember now which one. And we see different grains appear in different brightness because they are actually under different tilt. The lattice planes are differently inclined with respect to the parallel arriving primary beam. And for example, if we plot for such a very dark grain, which is in channeling mode, the corresponding diffraction pattern, then we see that the primary beam direction, which is indicated here by this little white cross here, is actually exactly on a Kikuchi line. That means we will get channeling, while for a grain which is here very bright, the primary beam is exactly inside of a Kikuchi band. And that will lead to strong backscattering intensity. By the way, these diffraction patterns we can, of course, not see because we are not having a detector on top of the sample. We are not doing back diffraction. I calculated these diffraction patterns from the measured crystal orientation, which we measured by electron backscatter diffraction by EBSD. Now, and let's look for other situations. We have all kinds of intermediate different orientation situations, and therefore different brightnesses. And now our aim will be later on to tilt one grain after the other into these channeling conditions in order to see what kind of defects are in there. All right, so then let's see how this is realized in an SEM. And for this here, I show you a cross section through an SEM. Here is the electron column with the electron beam here. And we have this is the chamber, and in this chamber, we will place the sample below the electron beam. And the first technique, the first diffraction technique, which will come along, is usually the EBSD technique, electron backscatter diffraction technique, which is using an EBSD detector mounted here to the side. And we place a sample strongly, strongly tilted with respect to the electron beam, and then the electrons are backscattered towards the detector. And on this detector, we see a typical EBSD pattern. And from this, by then scanning over the sample, point by point, and measuring all these EBSD patterns, we are able to create this well-known orientation microscopy images, which are very powerful for many things, but that shall not be the topic today. In order to do ECCI, in order to obtain the channeling contrast, we use a different detector. We use this detector, the backscatter electron detector, which sits directly under the pole piece, and we move the sample very close to it in order to record as many electrons at as much intensity as possible on this detector, usually in the order of some 7 millimeters or so. Now, you should know the backscatter electron detector is only measuring the total intensity being backscattered. It is not pixelated, and therefore we just get one signal, while on an EBSD detector we have a pixelated detector, and we really measure for every position how many electrons arrive there. But that's also for the BSE detector not our aim. And now how we will use how do we use the BSE detector? The first thing is, let's rock the electron beam over the sample. That's not possible with many microscopes. Some microscopes allow that, but it's also a technique which I will not further address. Anyway, I just want to show you again, if we rock the electron beam, and then for every incident, every inclination of the electron beam, measure the total backscatter intensity and plot it in a polar diagram over the inclination of the electron beam, then we obtain what is called an electron channeling pattern. And you see, this electron channeling pattern has very much similarities with the EBSD pattern in terms of geometry and even in terms of intensity distribution. The physics of both is in principle the same. This is the so-called channeling in pattern. This is the channeling out pattern, but that shall not matter. Now, more important for us is now, we will use these electron channeling patterns later on to decide for the correct orientation of my crystal. But the first thing is, usually we are not rocking the beam. In most microscopes, we are just scanning the beam in an orthogonal manner. And what we then obtain is a picture like that. And that's a typical electron channeling contrast image. And what does it mean? We, instead of rocking the beam, we are so-called rocking the electron, the crystal lattice. Yeah, every crystal has a different crystal lattice. And we see that some grains appear very dark. That means they obviously illuminated the crystal. The electrons obviously travel parallel to one of the Bragg angles. So they are traveling parallel to one of these dark cECCI lines, and others travel in a different direction. And we see already here in this dark grain, we see some fine white defects, and these will be the dislocations which we are later on interested in. Now, how do we get to this image here? What do we need to do to find out under which conditions is a crystal in Bragg condition? First thing is, we could just randomly tilt our crystal until it turns dark, and then we are happy. But then we don't know which lattice planes have created this image, and we even don't know is this the best observation conditions or not. So we do it differently. We do the following way. First, okay, that's maybe in the wrong order of animation. We will be able, as we have in most cases, let me go back. In most cases, we do not have access to these electron channeling patterns for a given crystal. So we don't know, as we cannot see this diffraction pattern, we also don't know which cECCI line is creating the dark situation here. But we can simulate these diffraction patterns. How can we simulate? So let me show you this. Let's say we want to know for this crystal here in the center, under which conditions does it turn so nicely dark? So the first thing is I make an EBSD map as you see it here. Then I select one grain, select this grain here. And from this grain, I obtain an EBSD pattern. And from this EBSD pattern, I obtain the crystal orientation, which I have indicated here. Now, from this crystal orientation, I calculate the electron channeling pattern using a special software. Actually, it's a software one software is the one which I designed for TOCA. So I calculate this electron channeling pattern. And now using this electron channeling pattern, I'm rotating my sample such that I will obtain channeling conditions. So using this channeling pattern, I calculate the position of the crystal in terms of tilt. And from this, I obtain the correct channeling conditions. So once again, go back here. I select a grain. I measure its orientation. From the orientation, I calculate the diffraction pattern. From the calculated diffraction patterns, I calculate how much do I have to tilt my sample. This sample tilt is placed to the microscope, and then I observe and get channeling. Good. So then let's have a look how this looks like, what we see then. So I show you first a couple work on stacking faults and dislocations, which is a work which I did in collaboration with Nahid Elhami, and we wrote, you will see later on, a large paper in Acta Materialia already 10 years ago, but you will see the reference later on. So imagine here, we will have a stacking fault in a crystal, which is just a planar defect, which comes here to the surface of a material, and then it goes down into the material. If we now look on the atomic arrangement on this hatched plane here, we'll find something like that. On top of the stacking fault, the atoms are in perfect alignment. So it's a perfect crystal. Then when the stacking fault intersects this hatched plane here, we actually see two partial dislocations, and they lead to the fact that the lattice below the stacking fault is shifted by a fraction of the atomic lattice, of the atomic distance, such that the atoms below the stacking fault are no longer at the same site as the lattice above, as the atoms in the lattice above. And if we now place our electron wave onto it, which I showed you already before, and we place it such that we are in channeling conditions for the perfect crystal, then we are exactly in backscattering conditions for the crystal part below the stacking fault. So up here, channeling, down here, backscattering. And if we now calculate the total amount of backscattered intensity from this crystal, we obtain a picture which looks like that. Or if we place it, that means let me put it here, where the stacking fault comes to the surface of the sample. Whoops, wrong direction. We get a very strong backscattering signal, and then the deeper we are below whoops, once again, the deeper the stacking fault sits below the surface, the more the intensity fades away, but it does not fade away homogeneously, but it fades away in kind of in wave. So very bright, then comes a dark line, bright, dark, so-called extinction fringes or thickness fringes, which depend on the thickness of the lattice of the stacking fault below the surface. And to show you that we really see that, I show you now stacking faults observed with ECCI. This is a picture taken by Surendra Makineni on a superalloy, and you see here lots of features. So this is, of course, with backscattered electrons. You see here, this is a 200 nanometer bar, and we see here all these structures which show this typical extinction fringes, bright, dark, bright, dark. This is a stacking fault standing under a certain inclination with respect to the surface. By the way, of course, we need to know under which conditions have we taken this picture. This here is our diffraction pattern, our calculated, simulated diffraction pattern, and we are exactly on this Kikuchi line here to obtain this contrast. And this is an 002 Kikuchi line. That means the diffraction vector is an 002 diffraction vector, which stands perpendicular on this lattice mechanism as in T here. But now let's go to the next typical sort of defect, and that is dislocations. And I put the same picture. Imagine that this would be a dislocation running through the material, and actually, again, I plot here a plane from which I would display you the typical atomic arrangement. You see on top of the dislocation, the lattice is perfectly arranged. Then comes the dislocation. That means one lattice plane is stopping here, and below the dislocation, the lattice plane is rearranged. That means here the atoms are in a wrong arrangement with respect to here. And same story if we place our electron beam onto it and we put it in channeling conditions for the upper part, for the part above the dislocation, then it's in backscattering conditions for the part below. And as a result, we see a dislocation line on a black background of the channeling, of the perfect channeling of the perfect crystal. The dislocation where it comes to the surface forms a very bright point and then fades away with a certain oscillation contrast as for stacking faults. Now let's look how this actually looks like. This is a typical diffraction. This is a typical grain from, in this case, from a BCC alloy, not from an FCC as in the previous case. And I have tilted this crystal such that it is in two beam conditions. Here you see actually the simulated diffraction pattern. The primary beam sits right on one of the Kikuchi lines. Which Kikuchi line is it? It is a 1 - 1 0 Kikuchi line. And that means the diffraction vector is standing perpendicular on this 1 - 1 0 lattice planes. And here is the diffraction vector. It's a 1 - 1 0, and it points perpendicular to this lattice planes here. Now, then the crystal appears very dark. And now we zoom into this little area here in order to see the defects more clearly. And what you see is then this typical picture here, all these beautiful long dislocation lines, some of them showing really this typical oscillation contrast, bright, dark, as I showed from theory. Now, we see here a number of dislocations, and I would like to point out what we see. But before that, let me shortly show you the width of such a dislocation line. Here on this picture is about 8 nanometer. This was taken with an older microscope. Our latest microscope, an SEM 450, Gemini SEM 450, allows us to reach about a 5 nanometer resolution of these images. Anyway, now let's do a quick analysis of these dislocations, as I did for the stacking faults in the previous image. And again, I use preliminary knowledge that dislocations in BCC materials all have a 1-1-1 Burgers vector and are often screw-type dislocations. So, and therefore I have plotted now the 1-1-1 directions into this, or I will plot them into this stereographic projection of this crystal orientation here. So let's start with these dislocations, which are the most prominent ones. Yeah, just this red trace, I plot it in here, and I find that the dislocation line is actually running right through the 1-1-1 pole here to the 1-1-1 direction. So this could be a 1-1-1 crystal direction. Now let me go to the next one, and that is these horizontal ones. I plot it here, and I find, not surprising, it's again cutting right through a -1-1-1 direction. I plot the next one, and this one I cannot plot for you because it's just corresponding to these little white dots which we see here. Here's one, here's one, here's one, and so on. That are dislocations which are sticking right out of the plane, and that means they are in the middle of the pole figure. They are 1-1-1 directions. And finally, we have one last set, and they are almost invisible here. They are very faint traces of dislocations which are almost invisible. And if we plot this trace, again, it goes right through the 1-1-1 direction. And now if you are a TEM person, then you know that there is a rule in TEM. Dislocations are invisible when the product, the scalar product of the diffraction vector, which is 1-1-0, and the Burgers vector is 0. So G dot B equals 0 means the dislocation is invisible. And now if we assume that this is a screw dislocation and that it runs parallel to 1-1-1, then we exactly find that the scalar product of that and that is 0. And that's why these dislocations are invisible. So what we have done here now with one picture just is a dislocation analysis, including Burgers vector analysis for at least one set of dislocations. Coming a little later. So how do we get these beautiful pictures, which I have shown you? One of the tricks behind it is that we need an image, we need to have almost parallel illumination. In TEM, excuse me shortly, let me just switch back. In TEM, we know we take images of dislocations under parallel illumination. And that means in an SEM, we need to have we do not have a convergent beam, but we need to have a parallel beam. That is something which is not so common in an SEM. You would usually like to have a convergent beam in order to have a small spot size. So of course we want to have small spot size in order to have good resolution. We also want a high beam current. How does a high beam current go with a small spot size? That's also a contradiction in principle. And finally, we need, in order to record the image of all of that, a sensitive and a quick backscatter electron detector. And all these conditions are fulfilled at the same time by the very particular construction of the Zeiss Gemini columns. And here I show you one of these typical columns, which is a very special arrangement here. This is actually the latest Gemini columns have a double condenser and then the Gemini lens. And this Gemini lens leads to the fact that we have a crossover-free illumination. The last crossover is far up here, and that means we have a very long working distance and therefore a very parallel beam. And that is one of the most important features of it. And then, of course, in order to do the controlled illumination, we need software, which in this case, in my case, is the software TOCA, which allows from a measured orientation, EBSD measured orientation, to obtain the correct the correct tilting conditions. That means at best we combine all this with a eucentric tilt stage, as it is usually common for focused ion beam instruments, a 6-axis stage, which allows us to do free and easy tilting. And then, of course, very important and not topic of this lecture here now, you need very particularly well-prepared samples. They must be flat, they must be strain-free in the surface, and that is very particularly difficult because we are looking only on the first maximum 100 nanometers of material, and there you don't want any scratches and nothing from surface preparation. Okay, and then if you do it all right, then you get these beautiful pictures as you see it here. You see in this particular case, let me move myself away here. This is a planar slip in a high entropy alloy, and you actually see here a lot of dislocations, which each of them shows this typical oscillation contrast. Here you see that the dislocations oscillate back and forth, which is just this typical effect of an electron beam penetrating into a lattice. And then you see that they are on slip planes. So we have intense planar slip. And we see something more in this picture. We see like here and here and here at many other places that the dislocations are paired. So I just zoom in. You always see dislocations are paired. And this tells us something about the behavior of this material. It could be, for example, that I have that I see either that I see a dipole following each other, so a plus and a minus dislocation, or two positive dislocations running one after the other. So we are able to, or we, from the appearance of this dislocation contrast, we could conclude what kind of dislocations do we have here? Do we have a short range order, long range order in this material? Is it really a high entropy alloy, for example? Yeah, and we can use a software, EMsoft, which has been published by Marc de Graaf, which allows to calculate under certain conditions the contrast of these dislocations. So if you take good pictures, as I show you here, and you know which kind of diffraction vector you have, and you know what kind of lattice planes you have, then you can use the software EMsoft and calculate the contrast of these dislocations, screw dislocations, edge dislocations, and see the oscillation contrast is different in the case that you have a positive or a negative Voges vector. So in principle, by modeling these dislocation images, we are able to understand more details of the diffraction images, of the electron channeling images, and then, of course, of the material. Okay, so let me show you a couple of pictures before I come to more worked out examples. Here we see first a couple of subgrain boundaries in a high strength aluminum alloy, 7075 aluminum alloy. This is a typical picture here. And what we see here is actually this typical image of crossing. Now you should have my picture of crossing dislocation lines. Yeah, and there's one set of dislocations lines like that, one set of dislocation lines like that, and that means the crystal below and the crystal above this this dislocation network is actually slightly misoriented, and that's a typical picture of a twist grain boundary, as you see it here. You have screw dislocations, crossing sets of screw dislocation, which lead to a twisting of the lower and the upper crystal. By the way, these white features here, these strongly overexposed white features, are actually particles which are responsible for the hardening of this high-strength aluminum alloy, and they are containing copper and zinc, and therefore are much stronger diffracting or much stronger scattering than the rest of the material, and therefore they are overexposed. Let's look at another picture. Here again, the strong particles here, yeah, which are appearing white. But what I want to point out is this dislocation, these dislocations here, which are in this case not a twist grain boundary, but a tilt grain boundary. And we know a tilt grain boundary consists of sets of screw dislocations next to each other, and they make the rotation like that one. So, okay, so we see these beautiful twist grain boundary, and here you see another subgrain boundary in the same material, and this subgrain boundary is created by dislocations, and these dislocations are decorated by small precipitates forming, nucleating on these dislocations. So here's another, no, it's not another picture. This is showing how do we do now, what's the workflow to obtain this ECCI images, or better to do controlled ECCI. We first measure, I mentioned it already a couple of times, but let me conclude that here. We first measure the crystal orientations using EBSD. For that, we have the sample at 70-degree tilt. So we obtain the crystal orientation. Then we tilt our sample from 70 back to normal, horizontal. Then we see, for example, a typical image here, nano twin. Matrix is in channeling conditions, the twin is in backscattering condition. Then we simulate using this computer program Toka. We simulate the diffraction pattern for this condition here, for the untilted condition. And actually we can, oh, this will not work here. Wait a moment. I need the laser pointer off. Yeah, now I can click here. So now the software allows you to calculate the tilt angle under which you obtain channeling conditions. As you see it here, we can model this the tilt angle, okay? And then we stop at the moment when the primary beam is right on top of a Kikuchi line. And then from that, we determine how we need to tilt our sample. So here is now a tilt of 16 degrees, and then we find out now this little twin here is turned into channeling conditions. Okay, and then we can do this with every grain by measuring EBSD and then using, we have studied many different materials already using ECCI, and we have, in the metals, we have looked on superalloys, we have looked on steels, on aluminum alloys, magnesium alloys. They are difficult, as I mentioned. Tungsten goes extremely well as it is such a heavy material and scatters very strongly. It gives pictures like in TEM. We have looked on semiconductors, on gallium nitride, gallium arsenide, cadmium telluride. Silicon is more difficult because of its lightness. Then we have looked on different ceramics, strontium titanate, silicon nitride, which is a very light material. It's difficult imaging, but going down in acceleration voltage, it gives good images. And then we have looked on different minerals as well, like pyrite and even quartz, which is actually another challenge because it's not well conducting. It's actually extremely badly conducting. Therefore, we need to apply a thin coating of carbon to image dislocations in quartz as well. And last slide, I'd like to compare ECCI with TEM. So ECCI is clearly a TEM-like characterization of dislocations and other defects. Because we are, whoops, why is that coming up already? Because we are observing the dislocations on a bulk sample, we have the chance to observe these defects in a more natural arrangement. That means no stress reliefs during preparation of this sample. Also, we can do more easily in situ observations, like annealing. I skipped over an example, or deformation. I showed you an example. Much easier than doing this in TEM on thin foils. And then we can see dislocation densities up approximately 10 to the 14 per square meter, which is already quite a high amount of deformation. And finally, let's compare some features of ECCI with TEM. The lateral resolution of TEM, of classical diffraction-based TEM, is of course much better, about 1 nanometer compared to maybe 10 nanometer in ECCI. As I mentioned, we see 5 nanometer images of dislocations. The depth of observation in ECCI, we look about 100 nanometer below the surface, which is pretty much the same area we see in TEM thin foils, which are also between 100 and 200 nanometers thick. The observable area is, of course, much bigger in ECCI, as we can use a bulk sample, and this can be rather big, yeah? While in TEM, we have thin foils, which usually have much smaller areas of observation. And of course, the sample is a bulk sample, which creates all these advantages compared to a thin foil for TEM. And we have as I mentioned earlier, we have published all this work, or some of that work, including theory, in a paper from 10 years ago already. So thank you very much for your attention, and I hope I get the chance to answer questions either by email or direct in person. Thank you very much.
Okay, so we are back in the room, as they say. Guys, thank you ever so much for that. That was genuinely fascinating. I loved every second of it. We've had loads of questions, so I'm going to waste no further time. I have questions of my own, but I'll ask the audience ones first. The first question was, can we study interfacial defects with this technique? I think I know the answer, but please, Stefan.
Yeah. First, thank you very much that so many people are listening and actually are also asking questions. This is wonderful. And yes, interface dislocations, interface defects are actually a topic which we have worked on quite intensively already. That means if you see an interface, you tilt your crystal such that one of the two crystals is in channeling condition. And then you see, for example, the interface dislocations in quite a nice manner as we are used to see them from TEM, though with the limits in resolution, as I mentioned already. You may have a resolution, let's say, if we are not going for the extreme of 10 nanometer, that means everything which is much closer together than 10 nanometer we will not see. But everything else, it's quite a nice technique to study these defects, indeed.
Okay, good. Thank you for that. So another question is, could you what does it say? Could you be precise on how you select the dark or bright parts of the ECP pattern to produce the ECCI image? So maybe they just want a very quick kind of precision.
That is a very important question because, of course, I did not in all details explain the process. What we do is we first measure the orientation of a crystal. We use EBSD for that in the meantime.
Yeah.
And once you have this orientation, you enter that into the software TOCA, which I mentioned shortly in my lecture. And this TOCA gives you a simulation of the diffraction pattern under the conditions of ECCI. That means not under 70-degree tilt, what was EBSD, but under horizontal tilt. Yeah. And that's a situation where you see the ECCI. And now this TOCA allows you to simulate the diffraction pattern under different tilt angles. And that shows you when do I reach the situation that I'm exactly crossing with the primary beam direction one of the channeling lines, which is the same as the Kikuchi lines. And in this moment, you read out from that software what's the tilt angle to reach the situation. You transfer this to the microscope, and then you obtain, actually, without seeing the channeling pattern really in your microscope, you obtain the channeling conditions. So it's a couple steps process. EBSD measurement first, then simulating the ECCI, the channeling pattern, and then obtaining the channeling contrast image.
Okay, good. Thank you for clarifying that.
Yeah, right. It's quite a complex process, maybe. Yes.
Yes. Yeah. Right. Okay. I'm sure people will appreciate that. Someone has asked a question. They work on a semiconductor called cadmium zinc telluride. Could this technique help them?
Absolutely. Cadmium, zinc, and telluride, they are all very strongly scattering materials because they have quite a heavy atomic number, quite a high atomic number.
Sure.
And usually they create very nice lattices. And that means you see the dislocations really lighting up very strongly. I have worked on cadmium telluride solar cell materials, and we get very beautiful dislocation images from this material. Of course, always in the limits of the resolution of the technique. That means if you have, let's say, grains of at least 100 micrometer size, you can very beautifully study that. Even smaller is possible, but the smaller they get, the more challenging the technique gets, of course. Yeah.
Of course.
But defects are beautifully seen in these microstructures, in these crystal structures. Sorry.
Okay, good, good. They were also asking about where they could do a test run, but I guess that's a question for maybe a follow up on offline. The second question, another question. Sorry, would there be any interesting observations at lower kV? Because I think I noticed from your presentation you typically do this at very high kV. So is it normally kind of 30 kV?
Yes. Give me the chance to answer with a couple sentences. If we run this microscope, particularly the Gemini 2, and I think also the single condenser microscope, at high voltage, then we get the smallest convergence angle. We get the smallest, that means the best parallelity of the beam, and we get the smallest beam current, and at the same time also the highest brightness of the beam. So these conditions are ideal for ECCI.
Sure.
But if you have light materials, everything lighter, let's say, than titanium, magnesium, silicon, all the oxides, all the minerals, the beam goes too deep into the material and you get quite a scattering, and you are losing in resolution when you go with high kV on a low atomic number material. That means it's necessary to drop then the voltage, and that's what we regularly do. First to 20 kV, then magnesium gives very nice images. But if you want to look on whatever, minerals with lots of oxygen inside, or silicates or so, then you drop even to 15 or 10 kV to still obtain proper resolution. And it's becoming more and more difficult, because also on minerals you need a coating. So you must find a compromise between dropping the voltage and being still able to go through the coating to see the results. Yeah.
Sure.
But indeed, low kV is quite an important option for ECCI. Yeah, right.
Okay. The question goes on to, I think what the question is asking is whether you've ever done this using, because I'm assuming you've done this with the insertable backscatter detector that's right under the pole piece.
Right.
Correct.
That's what we do. Yeah.
Because I know that on some systems with the Gemini column, there is the in-lens, the ESB, the sort of in-lens or in-column backscatter detector that's optimized to work at low kV, sort of 3 kV and below. Have you ever attempted to use that detector for this?
Indeed, yes. We have even done, even on a steel, where it would not be necessary, we have taken this in-lens backscatter detector and worked at 2 kV and got very strong contrast, actually. But we haven't explored this yet much.
Sure.
The channeling contrast is quite amazing, but it's overlaying to a strong atomic number contrast. That means we see, for example, very different brightness for carbides versus the ferrite in a steel. That means we are mixing channeling contrast with a strong atomic number contrast. And the channeling contrast, of course, then comes only from a very small first couple nanometer layer of the material. That means defects may not be that easily visible. We haven't explored it yet, but we saw strong contrast, I should say. Yes, indeed.
Okay, good. Well, I think that definitely answers that question. And of course, ESB stands for energy selective backscatter detector.
Yeah, right.
Sure, you would want me to point out. Good. That's a perfect answer. So thank you for that. Maybe time for possibly 1 or 2 more questions before we wrap up. I think someone had a question about the stage. So the stage you mentioned, you must have a 6-axis stage, which I guess is standard on the Gemini sims these days. And I'm assuming that is a ZEISS stage. That's not a special stage that you have to buy especially for this. Is that correct?
Yes. Right. Yeah, that's a ZEISS stage. And 6-axis mainly makes the process very easy because of the compute-centric stage. So, you can move your sample up and down and always keep it in the same position.
If I may add up to that, that's fully correct. Important is the eccentricity of this stage. That means while observing the image, you can tilt the sample and keep the dislocations or any defect we are interested in inside. So you see how the contrast changes from backscattering to channeling. while you're observing these defects. And then you can stop right at the correct angle, which you usually do not get by just a simulation of the channeling pattern. You always need to adjust a little bit. Yeah. Of course, these 6-axis stages are a little bit uncommon for normal SEMs. They are very common for FIPS, but
Yes.
you need to get them as an additional option for a normal SEM if you want to have the access to this eccentric stage tilting.
Right. Okay.
But Rishi, you have maybe the experience that you can also do it with compucentric tilting, which is a little bit less comfortable. But if you don't have a stage with just a eccentric tilt, you can still use compucentric tilting. Yes.
Sure.
You could, but as you pointed, when you're looking at a very small area, it's much easier to have the eccentric stage.
Yes, correct. Absolutely. Okay. We profit of it very much. Yes.
Okay. Yeah. No. You want to make your life as easy as possible, right? When you're trying to target a very specific area. So, so I'm assuming that this approach could be applied if you had a crossbeam, for example, which has a Gemini 2. So there you would have the 6-axis eccentric stage and the Gemini 2 with all of the correct detectors. So if anybody has a fib out there, they can immediately start doing this technique.
Absolutely. Right. Yeah. We have equipped all our SEM with double condenser with the 6-axis stage.
Sure.
Which makes it a little bit more expensive, but it's fantastic for ECCI, of course.
Yeah, no, I appreciate that. I'm just thinking for the people watching out there who think to themselves, hang on a minute, I've got a 6-axis Gemini 2 column in my crossbeam. I can immediately start doing this. I mean, obviously they're already doing a lot of other things, I'm sure, but it's potentially something that they might want to explore. Okay, good. Well, I think we're pretty much out of time. We've sadly, we just run out of time. So, thank you. I'm going to say thank you, gentlemen. Thank you for everybody watching. If there are any questions that didn't get answered from the audience, hopefully you can follow up with people online. And I believe that this webinar is going to be on demand, which means that if you enjoyed it, you can rewatch it. If you enjoyed it and your friends didn't watch it, then please tell your friends. With that, I guess I'll wrap up and say thank you again, gentlemen. I hope you've enjoyed doing it as much as I've enjoyed watching it, and hope everybody else out there has enjoyed watching it. And have a lovely day.
Thank you very much as well.
Thank you.